When solving exponential equations, our goal is to get the base to be the same, and then we can set our exponents set equal to each other and solve. To do that, let's explore the idea of finding common bases or making bases equal the same thing. So I've written down some common powers for the first 3 or 4 bases here, and I have the base or the number 625 and the number 25. And I want to rewrite them so that they have the same base. What I'm going to do is I'm going to look in each column and see if I can find both numbers in the same column. And you can see here that for 25, I have both 25 and, or excuse me, for 5, I have both 25 and 625 as a power of 5. 625 is 5 to the 4th power, and 25 is 5 to the 2nd power. They've now been rewritten with the same base. I didn't change the value. If I were to type 5 to the 4th in my calculator, I'd still get 625, or 5 to the 2nd in my calculator, I'd still get 25. But now they're rewritten in such a way that their bases are equal. You'll find that sometimes with pairs of numbers, you'll have multiple options for your bases. For example, I see both 16 and 64 in the powers of 2, and 16 and 64 are powers of 4. So you have choices here. You can write powers of 2, which 16 would be 2 to the 4th, and 64 would be 2 to the 6th. Or you could use the powers of 4, 4 to the 2nd, and 4 to the 3rd. A factor tree may be useful, or some good old tried and true trial and error on our calculator until you get the hang of figuring out what common bases would work. Let's take a look at how this can be applied when we solve our exponential equations. I've been given this equation, and I see a base of 3 and a base of 9, and I want to be able to rewrite this so that they both have the same base. Now, I can use a chart like this, or like I said, a factor tree, or some trial and error, and you can see that both 3 and 9 are both in the 3 column. That's going to be our common base. 3 is 3 to the 1st power, and 9 is 3 to the 2nd power. I can replace 3 to the 2nd power. I can replace 9 with it, and I don't change anything because they're the same value. It's similar to if you were writing an essay and you replace the word with a synonym for that word. You didn't change the meaning of the sentence or the meaning of the word. You just put a stand-in in there. So 3 being replaced with 3 to the 1st does not change anything. Not a whole lot's happening on the left side of the equation. But when I replace 9 with 3 to the 2nd, any exponent that was in the original problem needs to be in parentheses, because that too will need to be distributed to both the x and the 28. Now that my bases are the same, I can set these exponents equal to each other. So that will give me x minus 4 equals 2 times x plus 28. And we're going to solve this equation just like we have done in previous courses. We'll distribute the 2 to both the x and the 28, giving us x minus 4 equals 2x plus 56. And then subtract 2x from both sides, or if you choose to move your x's to the other side, you would subtract x from both sides. Both should give you the same answer in the end. Negative 1x minus 4 equals 56. Then we'll need to add 4 to both sides. Negative x is equal to 60. Divide by negative 1 so that x equals negative 60. Now we can use this information to check and see if our answer is correct by plugging it into our calculator. To do that, You'll use the original problem before you did any changing of bases and plug negative 60 in for all of your x's. We'll plug the left side in first, and we don't particularly care what number we get. What matters is that when I plug the right side in, I want this same nasty long decimal. So 9 to the negative 60 plus 28. And since I have the same number on both sides, I know that I've done this problem correctly. Let's try another example. 4 and 64. If we looked at our chart, you would see that there's some options there. I could use 2 as a common base. 2 to the second power is 4, and 2 to the sixth power is 64. Or I can use 4 as a base. It does not matter which one you choose, whichever one comes to you first. So I'm going to use a common base of 4. 4 to the first power is 4, and 4 to the third power is 64. I'm going to rewrite my equation with my equivalent bases. So 4 replacing itself, not a whole lot of change. But 64 will be replaced with an equivalent number, 4 to the third, leaving whatever exponent was already there inside parentheses. Our bases are now the same, so we'll set the exponents equal to each other. X plus 35 equals 3 times x minus 3. We'll need to distribute that 3 across our parenthesis set. So x plus 35 equals 3x minus 9. And then move our x's to be on the same side, whether you subtract x from both sides or subtract 3x from both sides, giving us negative 2x is equal, or plus 35 is equal to negative 9. Subtract 35 from both sides, giving us negative 2x is equal to negative 44. And then finally, we'll divide by negative 2 on both sides. X is equal to positive 22. And of course, just like with our first problem, we can plug it back into this original equation here and get the same number on both sides, indicating that we are correct in our work. Now, both of these problems had bases that were integers or whole numbers. What happens when our bases are no longer whole numbers and they're fractions? Well, you're going to put your focus on your denominator to figure out what is the common base between the denominator and our whole number. And we know from our previous problem that we can use a common base of 4. 64 is pretty easy, 4 to the third. But how do I rewrite 1/4 so that it's 4 to the something? Recall back to our Algebra 1 curriculum where we learned about negative exponents. And we know that when there's a negative exponent, it has to cross over a fraction bar to change its sign. So if I had 4 to the negative 1 and I wanted to make it a positive 1, it would have to cross over the fraction bar and become positive. That's how we get 1/4. So whenever you see a fraction base, it's an indicator that you're going to have a negative exponent. So you'll focus on, well, 4 to the first power gives me my denominator, and then make that exponent negative to give you the fraction. In your calculator, you can check to make sure that you really did it correctly. We have 4 to the negative 1 and change it to a fraction to give us 1/4. So I know that they're equivalent. Let's go ahead and replace both of these common bases in for their equivalent number. 1/4 will become 4 to the negative 1, leaving whatever exponent was there in parentheses. 64 will become 4 to the third, leaving this x minus 1 in parentheses. Since their bases are the same now, I can set their exponents equal to each other. Negative 1 times 2x plus 2 equals 3 times x minus 1. It's time to solve. Distribute that negative 1 across your parenthesis set, giving you negative 2x minus 2. Distribute the 3 across our parenthesis set, giving us 3x minus 1, or sorry, minus 3. Now to solve it, we'll subtract 3x from both sides. Negative 5x minus 2 equals negative 3. Add 2 to both sides. Negative 5x equals negative 1. And then finally, we'll divide by negative 5 on both sides, giving us that x equals positive 1/5. Check it on your calculator to make sure that it is correct, and you're finished. Let's do another one with a fraction exponent. Again, our focus is going to be on our base and our denominator. So 3 and 9, I know that both of those can be rewritten as 3 to the something. 3 is just 3 to itself, to 1 to be itself. And 9 is 3 squared. So if I want it to be 1 over 9, I have to make that 2 negative. 3 will remain the same. It already had a base of 3. And 1/9 will become the equivalent number of 3 to the negative 2. And we'll leave x plus 1 in parentheses. Now that their bases are the same, we'll set their exponents equal to each other. 6x minus 2 equals negative 2 times x plus 1. We'll need to distribute this negative 2. 6x minus 2 equals negative 2x minus 2. We'll add our 2x to both sides. 8x minus 2 equals negative 2. Add 2 to both sides. 8x equals 0. And then divide by 8, leaving x equals 0. Check it into your calculator by putting 0 in for x, and make sure you have the same number on both sides to ensure that you did this correctly. Let's take a look at our last two problems. Again, our focus when we see a fraction is going to be off of finding a common base for any integer and the denominator. And 20 squared gives me 400, and 20 to the first power gives me the 20. So I'm going to use a common base of 20. As I said, 20 squared gives me 400, and 20 to the first power gives me 20. So if I want to make that into a fraction or cross the fraction bar, my exponent has to be negative. We'll replace 400 with 20 squared. And there was no exponent to include in parentheses. Replace 1/20th with 20 to the negative 1, and then put our parentheses around the exponent that was already there. The bases are the same, so we'll set our exponents equal to each other. 2 equals negative 1 times 7x plus 8. Distribute that negative 1 to give you 2 equals negative 7x minus 8. We'll add 8 to both sides. This is a simple two-step equation. And then we'll divide by negative 7 on both sides. So x will equal negative 10 over 7. For our final problem here, I have 36 as my base, or as my denominator, and 216 is the other number. So we need to figure out What number can I raise to an exponent to be 36 and 216? The answer is I can use 6. 6 to the second gives me 36, and 6 to the third gives me 216. So my common base is 6. 6 to the second gives me the denominator, but in order to make it a denominator, I'm going to have to make the exponent negative. And then 6 to the third gives me 216. We'll rewrite this, replacing 1 over 36 with 6 to the negative 2, and put our x plus 8, that was the original exponent, in parentheses. Then we'll replace 216, oopsie, with our 6 to the third power, and put the x minus 3 in parentheses. Now that the bases are the same, we'll set our exponents equal to each other. Negative 2 times x plus 8 equals 3 times x minus 3. We have some distribution to do on both sides. Distributing the negative 2 gives me negative 2x minus 16, and distributing 3 gives me 3x minus 9. I'll subtract my 3x from both sides. So negative 5x minus 16 equals negative 9. And then add 16 to both sides. Negative 5x equals positive 7. Last step would be to divide both sides by negative 5 to leave x is equal to negative 7/5.